We're just waiting for a few more people to join in, and then we'll get started.
All right, we're going to get started now. So welcome to our Emerging Trends and Technology Network presentation entitled Visualizing Fuel Injection Spray Characteristics that Impact Engine Efficiency, Emissions, and Performance. This is a presentation that is going to give some fundamentals on these concepts and some ways of actually characterizing these fundamentals in spray technology, but with a focus on high performance applications, which actually changes some of the environment that the sprays are actually going to behave in. My name is Paul Pozanauskas. I'm an associate professor at the University of Alabama. I work in the thermal fluids area and focus on internal combustion engines. And I'm joined here with Josh Biddle from University of Alabama, Jason Haynes, and Bruno Silva from Nostrum, and I'll let them introduce themselves.
Yeah. So hello, everyone. Josh Biddle, also associate professor from the University of Alabama in the engines combustion area. Yeah.
And I'm Jason Haynes, Director of Product Validation and Vehicle Development at Nostrum High Performance. And before that, I was engineer at Lincoln Delta Performance Engineering for about 25 years. So some of the performance side of stuff and the V8 side of stuff will be especially pertinent to me.
Hello, everyone. My name is Bruno. I'm an engineer here at Nostrum. I worked with computer fluid dynamics, but I also do some of the injector testing that we do in-house.
Great. So I started the conversation here, but I know the least about fuel injection of the whole group that's here. And I think Nostrum's participation here is to really help focus us on high performance applications. And our goal is to inspire the audience to pursue some of these techniques or partner with companies like Nostrum and ourselves to learn more about how these different parameters in fuel injection affect performance, especially when you start modifying them. So just a little overview on the agenda here. We are going to talk a little bit about how fuel injection affects engine performance and what affects the spray quality and mixing, and then how we can actually quantify those things. We're going to start with defining the key features of a injection spray, and then we're going to show some of the differences of the application between port fuel injected, gasoline direct injected, and diesel engines. And then we're going to get into the different techniques of how we can quantify and characterize that spray behavior, things like rate of injection, patternization, visualization, and then utilizing optical engines. And then finally, we'll summarize. This slide shows some basic characteristics of a injector spray. In the middle, you'll see coming out of the injector a stream of solid fluid. And then as that fluid progresses through the injection process, it breaks up into smaller particles. That process is called atomization. And then those particles become smaller as they progress through the injection. Ultimately, for all the applications that we're looking at, we need the fuel to vaporize and mix with air so that it can burn. So ultimately, what we're interested in is how long it takes and at what point does the fuel vaporize. But before it vaporizes, it breaks up and then progresses forward. And then the things that matter and how that process goes forward are things like the cone angle, the velocity of the injection, the size of the particles, the density of the surrounding air, the characteristics of the injector, like the hole diameter, the pressure at which we're injecting, and then other aspects about the ambient conditions like the temperature and humidity and so forth. So these are the three different applications that we're going to talk about. The top one on the left is port fuel injection. The center one there indicates a direct injected gasoline application, and the bottom would be diesel injection. While the spray characteristics are are described by similar parameters, they're quite different because of the different parameters at which they work and over the times at which they work. The table up in the upper right, or the graph, shows basically the window at which these injections could occur relative to the engine cycle. So at the top shows the different strokes, the 4 strokes of the typical engine cycle, where the first line is the top dead center of the breathing stroke. So you can see the overlap period, then the intake process goes a little bit past bottom dead center, then we get the top dead center of compression, and then the exhaust valve opens somewhere around a little bit after mid-stroke, and then we have the exhaust process. So in the port fuel injection, what we know about port fuel injection is it's about the most forgiving of the different types of injection, mainly because we can inject over a very wide, broad window. And in some cases, we have to inject over a wide, broad window to get enough fuel into the cylinder under the injection parameters that are utilized. In gasoline direct injection, there's basically 2 different types. One where we're going to be using a lean charge. And to get that lean charge to actually burn, we want to stratify it so that we have somewhat near stoichiometric mixture near the spark plug, and then it can progress to a more lean mixture as you move away from the spark plug. So that injection is going to happen somewhere around where spark timing would normally occur, a little bit before. We'll start that injection process. It's fairly short. It's going to be, roughly 20 to 30 degrees or something like that, running, in about 0.5 to 7.5 milliseconds, whereas a port fuel injection can go as long as 15 milliseconds. In a stoichiometric GDI, we want a homogeneous mixture. So we're going to inject early to mid-stroke on the intake stroke, and give that fuel a lot of time to mix before it gets to the point where we're going to have an ignition process. A diesel engine is very similar to gasoline direct injection, except for we need to inject in a shorter time period, and we're going to actually, that spray is going to actually be a burning, combusting spray. So it's very important that the characteristics of the spray facilitate low emissions and high efficiency. And in some cases, that's improved by using multiple injections, where you might have a pre-injection before the main injection and then a post-injection. That's showed in the bottom circle there. Characteristic-wise, the injection pressures vary quite dramatically. For port fuel injection, you might be somewhere around 7 or 8 bar. In gasoline direct injection, somewhere around 50 to 200 bar. And then diesel can be 10 times more than that. The durations, again, listed in that second row there. And then the drop sizes get smaller as you get to the higher injection pressures with smaller streams. And then the velocities also, the velocities are proportional to the square root of the pressure drop. So the velocities are slowest with the port fuel injection. They get higher in the gasoline direct injection applications, and then highest in the diesel applications. So go ahead, and we'll go to the next slide. So I think, go ahead, Bruno.
Yes. So as Paul mentioned, the injectors, on the spray, you have different geometries. And basically that geometry of your spray, it becomes what is called your spray pattern. It just shows you how the mass of your spray will be distributed. Some people refer it as the footprint of your spray. So in the picture on the right, basically, is your injector, and the red cones, those are the representations of your jets coming out from your injector. And this geometry of your spray, it takes into consideration many aspects. It takes into consideration the intake port and the combustion chamber geometry, as well as how the injector will be installed in your fuel rail, what is the clocking and what is the angle that it will be in relation to the engine. And it will impact significantly your engine performance and efficiency, as well it will change your emissions and can impact your drivability, cold start and idle and misfires, for example. If we go to the next slide, we're gonna be starting to talk a little bit about the spray pattern into a port fuel injector. Paul, do you wanna?
Sure. So in comparison, port fuel injection, most of our production engines are moving to direct injection because there's a lot of advantages to evaporating this, the fuel in the cylinder. In a port fuel injected system, much of the injection happens in the valve closed period shown on the left. And because the valve is closed, most of the fuel doesn't evaporate yet and actually hits the surfaces. Now, there are some advantages to that cools those surfaces, but if we're puddling the surface, let's say near a coolant passage that will continue to reheat that surface, we lose some of the cooling advantages of the evaporating spray. The fuel that puddles on the intake valve will cool the valve, which does have some advantages in keeping the combustion chamber a little bit cooler. But generally, we're not going to get as much benefit from the cooling that happens in the port evaporation as we would in the cylinder. So if you actually open the valve, the puddles will start to break up and flow into the port. And at that point, some of that will be in a liquid form from the puddles and some will be in a vapor form. Some of the injection, if you are injecting during the valve open period, can go straight to the combustion chamber. However, that's pretty unlikely because of the geometric path from the injector tip into the cylinder. In order for those droplets to get around the valve and then that opening unscathed and into the cylinder, they got to be around 20 microns in size. And as the previous slide showed, typical port fuel injection sizes are a minimum of about 80 microns.
Yes. So this in this slide, we're gonna show a few examples of the spray pattern in a few of port fuel injector engines. So we have an example for the GM LS engines. So the LS3 and the LS7, they are naturally aspirated engines, and we know that the injector, the spray from these engines, it shoots like collinear with the injector. But when they added the supercharger for the LS9 and the LSA engines, they had to change the angle in which the injector would be installed in the engine. So they had to keep the targeting of the intake valves. They needed to change the angle of the spray in relation to the injector to get to the same targeting. And another example is the Ford Coyote, which is a V8 engine, but it has like two intake valves. So in this case, it was selected instead of a single plume spray, it was selected twin plume spray, so you can target both intake valves at the same time. But as Paul mentioned, timing, and it's much more flexible on port fuel injectors. But if we go to GDI, that becomes more restrictive. Next slide, please. So yeah, so as Paul mentioned, your injection is limited in the intake and the compression stroke. And in those two strokes as well, we need to inject, but as well, the fuel needs to evaporate and mix with the air. And so it's very important that the spray interacts with the charge motion inside the combustion chamber, so you can have maximum efficiency on the mixing. So the video on the right, it shows an example of like an injector. You can see the injection happening And you can see that after the injection, you can see the spray, it starts to have that tumbling motion, which is the charge motion in this engine, for example. And the spray pattern is even more critical on the GDI engines because it can result in very severe consequences, which could be improper mixture inside of your combustion chamber, which will reduce your engine performance. But it can also lead to engine knocking, as well as excessive smoke and making your emissions worse. But if you have a spray that it is heating your walls of the cylinder significantly, that seal will remove the oil, the lubricants in the wall, which will increase the engine wear. And this is considering, if you consider that you're picking a different spray pattern, but also increasing the flow rate, all those consequences will be intensified. So it's very important that you keep a appropriate spray pattern into your GDI engine. Next slide.
These slides just show the different techniques that are used to control where that spray actually goes. So a lot of this is a little bit, that has been mentioned by Bruno already. But there's basically three categories of spray control, and we call those wall guided. That's shown on the left. In that case, the spray is actually guided towards typically the piston, or it could be a part of the combustion chamber to create a particular pattern. And then air guided. In this case, the video that was shown in the previous slide by Bruno very well illustrated how tumbling motion can guide the fuel droplets and influence their spray. In this diagram, we showed the tumbling motion with the yellow arrow, and then the green arrow represents a potential swirling motion. And then finally, spray guided, and that's where essentially we're using just the spray to control the progression of the fuel. In reality, all direct fuel injection systems use every one of these techniques at some level, and in particularly the wall guided typically is combined with air guided. From a geometric standpoint, the layouts are generally separated into what we call a narrow and wide configuration. Narrow means that the injector is close to the spark plug. That's generally reserved for when we're doing these stratified charge lean burn conditions. That's not always the case, but like if you look at the spray guided schematic on the right, we have the spark plug and the injector quite close to each other. That's what we call a narrow arrangement. And the other illustrated, the other schematics for the air guarded and wall guided would be a wide configuration. Our goal is, like Bruno said, to create an optimum mixture without fouling the spark plug or trapping fuel in crevices and so forth, where they would end up as an unburned hydrocarbon. And then what we say by an optimum mixture is dependent upon whether we're in the lean burn case, where we want a stratified mixture, or in a homogeneous stoichiometric case. So each one of the illustrations show an injection with the piston near top dead center. That would illustrate our lean burn case, where we're injecting during the compression stroke. And then the one on the right in each one of the different configurations would be our homogeneous charge case, where we're injecting with the intake valve generally open. It could extend into the beginning of the compression stroke.
All right, so I'll jump in now and talk a little bit on the diesel side. So for the diesel sprays, as Paul said, they're all fundamentally the same, but we've got a little bit different criteria for the diesel sprays because of the need or the close coupling of injection timing and ignition timing. You have less than 1 millisecond from start of injection to start of ignition typically. So while total fueling rate is going to be the primary driver of power level, the spray quality can make or break performance from an emissions perspective. So the complex injection dynamics that go through evaporation, mixing, and ignition are very fast, both time and then very short in space. The illustration here shows those same regions that were on the first slide of the primary breakup, secondary breakup, of evaporation, and you try to avoid it, but potentially wall impingement or piston impingement, depending on the injection time. Also, the spray pattern from the diesel sprays is more radial than axial. You might say the included angle is much larger for diesel sprays. This is another illustration of those same concepts, but this one with a reacting spray. So in the near nozzle region, we've got the primary breakup, atomization, potentially coalescence, but ultimately turbulent mixing that leads to the fuel air combustion. And the right is a very near nozzle. So the diameter of this spray is around 100 microns. You can very clearly see that intact liquid core, but within 200 microns of the injector, it starts to break up and you see the fine particles on the edge. Primarily at this point, it seems most of the OEMs manage the emissions through after treatment and focus on injector for performance. But these regimes of the fuel spray, it's important to study these for trying to make modifications without compromising emissions behavior. So that will lead us into the actual diagnostic techniques that we'll cover today. So there's 4 of them: rate of injection or injection quantity, which I'll cover, spray patternation, which Bruno will cover, and then spray penetration measurements, and finally combustion measurements. So we'll go through each of these, talking about the apparatus, the types of measurements you can get out of it, and some of the fundamentals that make it possible. So for the first one, got rate of injection measurement system here. This is a picture of our setup here at UA. Inside, you can't see it, but there's a tip of a diesel injector buried underneath there. This is a 6-hole diesel injector, and we're using force sensors to measure the rate of injection. So not just quantity, but rate of injection. So while total fueling rate is often the most critical parameter, again, for power levels, you definitely see in aftermarket high flow injectors with plus 50, plus 100% flow. That's typically going to give in the total quantity, millimeters per stroke, for example, or a steady flow rate of pounds per hour. But achieving more performance or maintaining emissions compliance really is coupled with this rate of injection. This is a sample bit of data here in the top right showing a brand new injector and an old injector that was pulled out of a vehicle with about 80,000 miles on it. And in general, there's not much difference, but this rate of injection profile, see the transient ramp up, a near quasi-steady behavior before a ramp down at end of injection. Maybe counterintuitive, but for short injections, we see a slight decrease in the duration. And for long injections, a slight increase, where the old injector seems to actually stay open slightly longer. So the significance of that can play a role in long-term performance. From a quantity perspective, the bottom right figure shows a sample of data where we numerically integrate under these curves and get a total quantity or milligrams of injection per injection at different injection durations and different pressures. And we can see how the old versus new compares. So ultimately, a failure would be a clogged nozzle or potentially a stuck open injector. But even before those happen, you'll have some change in performance like this. So how do we actually get those measurements? This is a kind of illustration of that. It's a cartoon of the setup where we have the diesel injector. The spray comes out and targets a force transducer. For those that might be familiar with cylinder pressure measurements in an engine, this is basically a Kistler force transducer that measures the dynamic force, which then can be related to the momentum flux with the equation shown there, with a slight delay to account for the transit time from the nozzle to the sensor. But relatively simple, but allows us to capture the rate of injection differences for all the holes of an individual injector and over many different repeated shots and characterize the differences. So here's just a sample of some of the raw data. The top left is the raw voltage straight out of the sensor for a 7-hole injector with the injection duration and pressure shown. The bottom is the filtered results of those. So we can see some differences in the quasi-steady rate of injection, though very repeatable rise rates. Just to illustrate some of this test stability, this is 50 injections where we inject nominally at 800 bar plus or minus 10 bar, and then showing kind of the correlation between injection mass and pressure, or rather that there is no correlation. We're controlling the system quite well and getting good measurements. The bottom right shows kind of a validation of the method, where we took a gravimetric basis where you inject, say, 100 injections into a vessel, weigh the total injected mass, divide by 100, and that gives you your milligrams per injection. You can see quite good agreement between those two methods. So that approach is useful for characterizing diesel injectors, but could easily be adapted for characterizing GDI or PFI injectors in future. Bruno, I'll hand it over to you for the next one.
Yes, so as Josh talked about the rate of injection, as I'm going to be talking about the spray pattern. So how can we measure the spray pattern? So we use this machine called spray patternator. The one in the picture is the Hexcel patternator that we have available together with a picture of a spray pattern. But if we go to the next slide, so those spray patternators, injector patternator machines, there are two types. There are mechanical patternators, which you're going to be collecting your spray droplets into a cells and doing a measurement after of that distribution, or you can have an optical patternator. You could have in which you do the injection into like a in a region where the spray droplets will disturb light sensors and lasers, which will generate your mass distribution, your spray distribution. So for the case of the Hexcel patternator that we have available, it consists of 253 cells arranged in a hexagon pattern as shown on the top right picture. And each cell is measured independently, and we use n-heptane for this test, which is similar to viscosity. And it has a special machining on the inlet of each cell to avoid as you're firing the injector, to avoid the droplets hitting in between the cells and splashing away. So basically how the test works, we dynamically fire the injector over this 253 cells, and we collected. Once one of those cells reach 80% of its volume full, the test will stop, and then it will read the transducer on each cell, and will generate your mass distribution as shown on the pictures on the bottom right. And with this, we can analyze how does the spray, the geometrical properties of your spray. We can look at the cone angle for the whole spray and the centroid. As well, we can look for the individual plumes of your injector. And if we go to the next slide, going back to the port fill injectors that we mentioned, we are able to, using the spray patternator, we can confirm the targeting used on the engines listed. So we could do the representation and an analysis of how the spray pattern will behave in your engine. As well as in the next slide, we have a very good example for how the spray pattern is really important on your GDI. So the spray pattern, normally it's not advertised with your spray. Normally it's the flow rate. And a lot of injectors, they have the same shape, the same type of electrical connector, same length. But as we can see on the picture, they have this injector that have the same outline, they have very different spray patterns. And on the spray patterns shown, the red dashed line, it is where the electrical connector is. So if we look at how the spray pattern, how the spray will interact with the engine, in the engine and the combustion chamber. So for the top one, we can see that the spray is symmetrical to the engine. But if we use the wrong spray pattern, which is shown on the bottom, we can see that the spray pattern is not symmetrical anymore in relation to the engine. But as well, we can see that one of the plumes on the top, it will like hit directly the cylinder head, which could hit, contact the spark plug, and which will cause can cause misfires, or it will definitely reduce your emissions and cause some of the mechanical wear that we are mentioning. But the spray pattern, as you can see, it's a cross section of your spray. And when we are testing it at ambient pressure. So it's very important to also like analyze how the spray will develop over time, as well as like in engine-like conditions. So that's what Josh will be talking about next.
Yeah, thank you, Bruno. Yeah, so as he said, the rate of injection rig shows how much fuel is coming out of the hole. The patternation shows the general distribution and is generally representative of how the spray might behave under low pressure, low temperature conditions. But in some of the different injection timing concepts that Paul talked about for the stratified or lean burn GDI or diesel, the sprays can be quite different than what you might expect. So this section will talk about how we can visualize the spray penetration behavior. So this video's, I'll talk more in detail on the next slide, but these are showing GDI injectors with the same supply pressure, but different ambient conditions. I'll get to what the colors mean in a little bit, but focus more on the shape and behavior of these sprays at this time. So in the top left to the bottom left, we have basically a low pressure, maybe a 3 psi boost, pretty low condition. Low temperature, medium temperature, not much happening here. But even with that, 30 degrees increase in temperature, you actually start to see some differences in the evaporation behavior, as Paul talked about being a critical behavior parameter. And the way you can tell that is in the color in the edges of the spray. So that color is indicative of fuel vapor, whereas the black is the liquid fuel. And we can really see that on the right two images. In the top right, this is again low pressure, but quite high temperature. And you see a dramatic difference in the spray where we actually can no longer see the different plumes. Rather, they collapse as you have plume to plume interaction, and the density of the ambient forces a collapse and a flash evaporation of that spray. In the positive, there's very little liquid penetrating past about half the video, so there would be almost no liquid accumulation on a surface, but very different pattern coming out of that than the original patternation might suggest. The bottom right is high pressure, high temperature, more characteristic of what the spray would look like for a later injection stratified operation. This video is actually slowed or sped up 2 times speed. So the penetration rate is actually half approximately of the others. So your dispersion in the chamber is quite a bit different because of that. So putting a little more details to this, that top left one might be a low boost, cool intake air condition, minimal evaporation, minimal jet interaction. The distribution should reasonably match the patternation results. Bottom left probably still matches the patternation results, but starting to get some evaporation. That top right, significant evaporation, plume collapse, very definitely not going to match the patternation results. And then finally in the bottom right, lots of evaporation, slower penetration, and the distribution is going to still again be different. We can do similar types of measurements for diesel sprays, for multi-hole sprays. So this is a visualization of a 6-hole injector in the top. In the middle is a 6-hole injector with 3 extra holes. In the bottom is 7 different hole sizes. So are those practical? Maybe not, but we can take measurements and quantify the hole-to-hole penetration rates in conjunction with the hole-to-hole rate of injection measurements and get data like shown in the top right. This is penetration, average penetration for different conditions, so different ambient pressures and densities. This back one is different shot-to-shot variations for a single hole, and this one is jet-to-jet or hole-to-hole variations for a single injection event. So you can see you have quite different penetration rates. So you can imagine a bias of fuel distribution, both based on the rate of injection, but also just on the spray dynamics. In the bottom right, you can actually see some of that rate of injection measurements for that variable nozzle, where we can clearly see the difference in total rate of injection, which corresponds to the penetration differences. So how do we get these images? The simpler one is this pressure vessel, where we have a high-speed camera looking inside a chamber that has a Lexan window, where we can pressurize this chamber to similar conditions that you'd have, similar density conditions that you'd have in an engine. There's a good literature out there that shows that a non-evaporating jet behaves very similar to an evaporating jet as long as the ambient density is the same. So in an engine, you'd have high pressure, high temperature. In this chamber, we have a different pressure to match the density. And then the high speed camera, we can capture these videos and post-process for the penetration rates. For the GDI images you showed, and then for the diesel ones that I'll show shortly here, we have a different measurement technique that we call rainbow Schlieren deflectometry. These are images captured in what we call our high pressure spray rig. You can see here in the image, there's a diesel injector spraying into a chamber, which can be pressurized up to 150 bar and 1400 Kelvin, conditions of a pretty significant boost, moderate compression ratio engine at TDC. And then we can supply pressure up to 2000 bar to diesel injectors as shown here, but we've also got a module for GDI injectors or even PFI injectors that can be equipped. Now, Schlieren is an optical technique that you may have been familiar with. I show here a sample image from NASA of seeing shock waves on supersonic jets. You've probably maybe also seen the shimmer above asphalt on a hot day. That's the light bending as it goes through density gradients in the air. In our case, we're looking at density gradients in the fuel spray. So the optics here in the bottom right, you can kind of ignore if you don't want to focus on that. And essentially we get just a beam of light that is collimated, meaning all the rays are going in the same direction. As they go through the spray, they'll get bent towards the dense fuel spray. Some of them will be blocked by the liquid. And then as they're focused down to the camera, we put a filter in the path, and the light ray that goes through the filter gets colorized, and then we can quantify that in the images. So in the video here, doesn't correspond to this filter, but in that case, the background is orange, and light that got deflected a lot turns blue, light that got deflected a little bit turns green. Oops. So with that context, we can hopefully make some sense of the GDI videos, but now also go on to talking about diesel combustion studies. So here's a video in that same chamber I showed, looking at a reacting diesel spray. So this is a modified diesel injector to have a single axial spray, but with the same geometry as a multi-hole nozzle would. We can see the liquid near the injector. This is just a thermocouple measuring the chamber temperature. But then we have the liftoff length, the distance to the flame, and then clearly a very bright sooty reaction zone at the jet head. This image, while it looks nice, is not very quantifiable. So if we apply that same high pressure spray rig, we can get these natural luminosity images that are nice to look at. But if we use some different high-speed imaging, including the Schlieren system, we can look at the fuel vapor region. The black is the liquid, the colors are the fuel vapor, and the color indicates how much deflection there was, which is related to the quantity of fuel. We can also use an additional optical diagnostic called OH star chemiluminescence. This indicates where the flame reaction region is. And then a third technique called two-color pyrometry, which is very similar to the infrared thermometers that you might use to get manifold temperatures or your forehead temperature. But if we take all three of those, we can generate composite images and see the spatial alignment with liquid, mixing, ignition, and soot behavior. And of course, they're high-speed cameras, so we can see the temporal evolution as shown here from a ignition kernel at the jet head to a kind of a sooty mess to ultimately a relatively clean flame as the soot was burned. We can capture hundreds of these injections and get data at very large different conditions. So here's two videos showing the natural luminosity and the composite high-speed image. So we see the natural luminosity is what your eye would see if it were a high-speed camera. Of course, this whole injection is only a millisecond or two long. You would blink and you miss it. But the bottom right is where we can process and quantitatively capture the evaporation, mixing, ignition behavior. And so qualitatively, we can look at different operating conditions, different fuels. So the left two are the same fuel called dodecane at different pressures and temperatures. The middle one has a higher pressure and slightly higher temperature, and we can see quite a brighter flame. There's more soot. On the right is diesel at the same condition as the middle. So diesel, pump diesel is less sooty than this dodecane, but in future application, we can test different fuels, different pressures, different injector geometries, and see how these qualitatively behave. But we can also look at quantitative differences, excuse me, still qualitative here, where we can look at different test conditions, different fuels, and different times, and see how the different evaporation, different mixing leads to different sooting behavior, different combustion performance. For example, here between heptane and this fuel in the middle, we see different liquid lengths, we see different liftoff lengths, we see different sooting levels across these conditions. So I know this is probably overwhelming to look at here, but you can imagine from developing a new injector concept, perhaps you want to understand how that impacts the combustion performance. So the final results here, quantitatively, we can see how ignition delay is impacted on the left, how the soot mass is impacted on the right. So on the left, we can see as you increase the pressure and temperature, you get shorter ignition delays, kind of independent of the fuel. On the right, we can see the sooting behavior is quite different between those fuels, but also between the conditions. And you have very different behavior between different conditions where you have a big spike in soot early on or a big spike later on. So connecting all this work to engines is a bit out of the scope of this presentation, but we've done work where we've cross-validated the observations in the spray chamber to engine performance as well. But as a bridge to that, the final topic for today will be Paul here. So.
Yeah, thanks, Josh. So a lot of great visualization techniques that give you a lot of insight into the spray. One thing that's missing in many of these is actual flow field that's created by the engine running in an unsteady environment. So our next work into the future is to utilize this optical engine that we've shown on the right. This shows in this particular case, a Hyundai V6 cylinder head. It's sitting on top of what's called a Bowditch piston. The cylinder is optical. The piston is tall and has an opening where we set a mirror. So at the bottom of that opening there, you see the white reflection of the mirror. And if you're looking at the right angle, you actually look up at the combustion chamber there. And then as the piston goes down, the cylinder being clear, we can also see the entire cylinder flow field. And then that piston, that Bowditch piston, sits on a regular piston on a run by a crankcase at various different engine speeds. So this allows us to have optical access inside the engine combustion chamber to apply many of these different techniques combined with the actual flow field. And one of our goals is to apply this, set up a modern Gen 5 small block on this particular application. And companies that are doing aftermarket optimization for power without degenerating emissions could utilize this resource to ensure that they're not doing anything counterproductive with their changes in the injector design. So the next slide shows a little bit about how the spray actually changes under cylinder flow field conditions. I borrowed this from author Saris Pereira. I'm not sure I'm saying that right. It's from the International Journal of Engine Research. They used an optical engine, and the combustion chamber is shown in the upper left slide there. And then the slides to the right of the upper left slide show the spray. Basically what they did was use a laser to illuminate the spray at a particular, in that particular case, a horizontal position. That those horizontal positions are indicated by the green lines in the second row to the left slide. And in the top row, the engine's not moving. So that's what the spray looks like coming out of the injector with no flow field or with a quiescent flow field around the injector. In the rows below, we're showing a light load case running around. Well, they're showing a light load case around 1500 RPM, and I think it was about a 50 kPa manifold pressure. And on the first row shows a illumination in the tumble plane. In other words, they have this laser sheet oriented vertically, and allows us to see the injector penetration down into the combustion chamber. The yellow line indicates the piston, and you can see how the injector injection structure starts to disintegrate in the mixing process from left to right, indicated by the crank positions under the drawings. So what we're really looking there at is how the mixing occurs and how the injection is spreading and how the flow field is actually affecting it. In this particular engine, we're expecting to see a tumble type condition, and that tumble is changing that or influencing that spray as the piston falls lower. The bottom two rows are horizontal plane illuminated patterns, and those are analogous to the quiescent patterns in the top row. And roughly the first spray there is about 4 degrees after top dead center, whereas the quiescent one, the first one was I think 5 degrees after top dead center, and then the second quiescent one's around 10. So that corresponds to the piston position around in the actual engine running around 11 degrees. And if I would focus on the third frame to the right on both the third row and the fourth row, you can see how different those spray patterns are from the quiescent spray at the very top. And that's due to the swirling motion that is distorting the spray in the combustion chamber as the engine is actually running. So it's important to understand the fundamentals of the spray, and I think all these different techniques that Bruno and Josh spoke about show those things and show how the spray behaves in a quiescent flow field, but it's a system with an airflow field that it has to interface with. And I think being able to combine the techniques in an optical engine that's running under representative conditions is important, and that's kind of where we're going next.
So I think that wraps it up. Just in summary, again, we kind of hopefully have demonstrated the fuel injection does have a large effect on the engine performance. and understanding the injector nozzle, the patternation, the timing, and engine geometry interactions are important. And by leveraging these quantifiable measurements of spray behavior can hopefully lead to better performance, while managing emissions for future engine component design. So thanks for attention. Happy for any questions. We've got contact information there for any follow-up questions after.
We did have a question in the chat, and the question was, in a dual injected diesel, what prevents the first charge from igniting prematurely?
Okay. So yeah, we typically call that the pilot injection. Is a pretty common way to manage combustion noise, and some with emissions control, but it's primarily the timing of it. If you inject too early, it will auto ignite independent of the main injection, but usually the separation between that first injection and the second injection is short enough such that the relatively lean mixture created by the pilot injection does not prematurely ignite, and the main injection would still control ignition. Hopefully that makes sense. Okay. Yeah. So the question: what are your thoughts on compensating for poor injection pattern with multiple injection strategies? Is that with GDI? Or I guess we can answer both. Bruno, you want to take a stab at the GDI, or okay? Yeah, very good. Make sure you're unmuted.
Yeah. Yes, I mean, you could, but it's kind of, you're limited on how much shorter injection you can make as well on your engine. And some of those, like as you mentioned, on the start of the injection, there are the atomization changes during the injection event. So if you're doing like a wrong targeting, but doing multiple, maybe you're doing with the start of the injection, you might have like a lower quality spray just because you're with the opening. So you might be creating other problems as well.
I'll just add to that. Oh, sorry.
Well, there are GDI cases, particularly for lean burn, where they will use multiple injections to try to create a lean end gas, so that the diffusion and mixing of the main spray occurs a little bit faster and a little bit more effectively.
Then I was just going to say that may help at lighter load operations where you may be able to manage, but at full load where you're just trying to get the fuel in there, that's almost shooting yourself in the foot.
Yeah. So what I was talking about was all light, so the lean burn's all light and moderate load at highest, but at full load, that's typically not done.
Yeah. All right. So yeah. So then in GDI engines, how does increasing injection pressure affect spray pattern or vaporization? I think it's similar for diesel and GDI, but sorry, put you on the spot, Bruno. Do you want to talk from GDI side?
Yeah. Yes, as you showed on those images, it is likely that with the higher pressure, your spray pattern will get narrower because it will be the interaction between the spray plumes will bring the spray pattern closer. But it does help with the vaporization because you're injecting at a higher pressure, you're increasing the speed, which improves the breakup process of the droplets.
Yeah. So again, from the diesel side, it's very similar. The faster the jet, the more penetration, usually the slightly narrowing of the angle, but it can lead to better atomization breakup. Though in the diesel side, it's liquid length, or the evaporation is almost independent of injection pressure, because more speed means more entrainment, means it evaporates at the same rate. It's not exactly for GDI though.
The other thing to keep in mind is for the same size injector, if you increase pressure and you still need the same unit mass of fuel for that injection event, your injection pulse width will have to be shorter, compensate.
Yeah, and then you can get into issues of shot to shot repeatability. As the pulse width gets shorter and shorter, the consistency of the quantity per shot can deteriorate. Thanks for the questions, anonymous attendee. Yeah, any other questions?
Thank you, guys. If there's no other questions, we can wrap it up.
Very good. Well, thanks to everyone that attended.
Thanks for attending.
Thank you.
Are we making these
Thank
notes available to the attendees if anybody wants to see the?
Yeah,
The-
I'm happy to. If anybody wants, sorry, Nicole, you're.
I was gonna say the recording will be available online. I posted the link earlier in the chat. I'll put it in there again real quick, just so that if you do want to access it later, it'll be up here in a little bit. We've got a few others to post as well, but you can access this recording there.
Very good. Yeah, and if anybody wants the slides, I think can email me or any of us and can share.
Thank you.
Bruno, Jason, thanks again.
Thank you.
Thanks, guys.
you.
Nicole, thank you.
Have a great
Jericho,
day.
thank you.